Hello all. Now we know embedded system is the heart of the devices which we see in the modern world. If we assume embedded system has a brain inside, that is, microcontroller. Let's understand it better. Welcome to Cocowatt Media.
So, what exactly is a microcontroller? In simple terms, a microcontroller is like a tiny computer. It's a small, integrated circuit, often just called a chip, that can perform specific tasks, like reading sensors and control motors, or lights. As like a brain in human system, microcontrollers sense the needed parameters, process and tell the electronic devices what to do and when to do it. How does it work? Just like a regular computer, a microcontroller has several core parts. A CPU, memory, and input/output pins. The CPU, or central processing unit, is the part that does calculations and runs programs. Memory stores data and instructions for these tasks. And the I/O pins connect the microcontroller to the outside world, where it reads sensor output, controls lights, or communicates with other devices.
Microcontrollers are built on specific architectures for organizing components. Two main architectures used are the Harvard architecture and the von Neumann architecture. Let's compare these.
Harvard architecture. Imagine you are controlling a robotic arm in an assembly line. With Harvard architecture, the program instructions for each arm movement and the data, like position or sensor readings, are stored in separate memory areas. Since the CPU can access both instruction memory and data memory simultaneously, it can quickly read the next instruction and adjust the arm's position without any delay. This makes Harvard architecture ideal for time-critical real-time tasks. Von Neumann architecture. Now, let us take the example of a simple temperature sensor system in a thermostat. In this case, speed is not as critical, so the microcontroller's single memory can store both program instructions and data. When the CPU needs to check the temperature reading, it accesses the shared memory, alternating between reading instructions for checking the sensor and reading the actual temperature data. This can create a slight delay compared to Harvard. Since von Neumann architecture uses a single memory for everything, it's simpler and often more cost-effective, making it great for devices where speed isn't the primary concern. Let's look at the parts you'll find in most microcontrollers and how they're organized. These components are designed to work together, so the microcontroller can process information, interact with other devices, and use power efficiently. Central processing unit. The CPU is the microcontroller's brain, responsible for executing instructions. It has three main parts. The arithmetic logic unit, which performs all the mathematical and logical operations, like addition or comparisons. The control unit, CU, which manages data flow and coordinates activities within the CPU. And registers, which temporarily hold data, addresses, or instructions being processed. Memory. Memory typically includes three types. Flash memory stores the microcontroller's program code and keeps it even when the power is off. It's where the firmware, the instructions that tell the controller what to do, are stored. RAM, random access memory, is used as working memory, where data currently in use is stored temporarily. However, it's volatile, so it loses all data when the device is powered off.
EPROM is another type of non-volatile memory, useful for storing settings or data that need to be preserved even after power is lost. Buses. Buses are pathways that allow data and signals to move between components. Microcontrollers typically have three main buses. The data bus, which transfers data between the CPU, memory, and peripherals. The address bus, which carries the locations of memory, where the CPU reads or writes data. And the control bus, which carries signals that manage the microcontroller's operations, like turning peripherals on or off. Peripherals. Key feature of microcontrollers is their built-in peripherals. These are additional components that expand the microcontroller's capabilities and help it interact with the outside world. Some common peripherals include timers to keep track of time or perform actions at specific intervals. An analog to digital converter, a DC, which converts analog signals, like those from sensors, into digital data. And communication interfaces like UART/SPI and I2C, allowing the microcontroller to send and receive data from other devices. Clock and power management. The clock in a microcontroller provides timing to synchronize operations. A faster clock speed allows for more instructions per second but also uses more power. Power management is especially important in battery-operated devices, where low power modes, like sleep and deep sleep, help save energy.
In short, microcontrollers are the silent workers powering so much of the technology around us, bringing intelligence to the simplest of devices. Whether you're an engineer, hobbyist, or just curious, understanding microcontrollers is a gateway to the world of electronics and computing. Cocowatt helps to bring you these technology as simpler as possible to your hands.